I think Pavel is also back.
Pavel will come.
I'm
more confident.
Just make sure we are.
You can see because he came yesterday back from home.
I see. Okay, looks like we are like. Okay, so today, sorry about having this lecture on a holiday. I would put the blame on Renal. This is a topic I wasn't even planning to cover, but I think it's a good thing to cover. And every time I go over this, it's still quite miraculous that it works out. So, like in fact, the previous two lectures, there's going to be a large setup. Okay, for this, the final proof is basically going to be like you sample and then you're done. So, but it's a setup to get the problem to that form, and it's rather miraculous that the whole approach sort of works out so cleanly. So let me just do a brief recap. Only things that are necessary for today's talk, in fact, some of them will not even be necessary, is that we've been dealing with expanders and so on, and the intuitive notion is that the expander is like a sparse version of a complete graph. It has all the properties of a complete graph, except that it has far fewer edges. So it has a linear number of edges. And typically, when we talk about sparse graphs, what we mean is the number of edges being linear in the number of vertices. Okay. And we sort of were working with this notion that an expander is like a complete graph by basically saying that as a random walk matrix, there is this nice decomposition that we have where it's like a convex combination of the random walk matrix for a complete graph plus some error term. And this error term is something that you can control. Okay. And today, one of the things that we're going to be focusing on is something that I mentioned earlier, but we never really used it that much, which is the bilinear form associated with the matrix. Right? Given any matrix M, you can always talk about this bilinear form, which is you take an X and a Y, and then you just return X transpose M1. And we were doing it initially to come up with this eigen decomposition and stuff. And today we might actually flip things around a little bit. Previously, what we were doing was we had a certain matrix of interest, and then we wanted to know what is a bilinear form corresponding to this matrix. In today's thing, what's going to happen is that you will have a certain bilinear form of interest, and you would want to know what is the associated matrix for this. Okay.
When were we trying to understand the bilinear?
So in the sense that when we defined our own artificial inner product and we had a stationary distribution, etc., there we did this, but not really very intensely. But today, the focus is really going to be to, in fact, rather than bilinear forms, I'll talk about the quadratic form, which is you just set X and Y to be the same vector, X. Okay, so you look at X transpose MX, but I want to look at it from the reverse direction. That is, I tell myself that, look, I have a certain quadratic form I'm interested in. What is a quadratic form? It's just a degree 2 polynomial such that every term actually has degree 2. So there are xi squared terms and xi xj terms. Okay, so you have that's what a quadratic form is. And I would like to know, can I write this as X transpose QX, where Q is some symmetric matrix? And there is a very natural candidate for this. Because X transpose QX is basically going to be xi xj qij. If I and j are equal, then that's what you're putting on the diagonals. But when I and j are unequal, it splits as two things. So you just put half on either of them. So there is a very natural.
Unless you're in GFP.
Yeah, we are all realists. I mean, this is all reals and complex numbers here. So there is no things becoming zero. So there is a very natural associated to a quadratic form. There is a natural symmetric matrix. And much of what we are going to do today will be from this perspective. That is, there will be a particular quadratic form that will be very crucial. And we will just build a matrix that captures this quadratic form. And it will just turn out that that matrix has a bunch of beautiful properties that we can then use. Okay. So let me just start talking about what is a sparsifier. Today's lecture is going to be of a specific type of sparsifier called spectral sparsifier, but what are sparsifiers in general? So the typical setup is you have some undirected graph that is given to you, and usually we assume that this graph is connected. Okay, you have some connected undirected graph given to you. What we want is to choose a subgraph of this graph. Okay, but I'm willing to reweight the edges. So you take a bunch of edges from G, but take few edges from G. On each of those edges, maybe you add your own, different weight or something. And now you have a weighted subgraph H. Okay. And you would like to say that H in some sense approximates G. Okay. The notion of approximation is what will tell you what sort of sparsifier you look at. It's called a sparsifier because you would like H to be far sparser compared to G. Like you want H to only have order n edges, even if G had like n squared edges or something. Okay.
So this approximation is always according to some question.
Yeah. So there are many guises in which this approximation is studied. Spectral sparsifier is going to be one specific instance, but I'll talk about how this sort of classically came up. And it was classically defined by Ben-Sur and Kargar. Okay. Probably in the 80s or something, where they spoke about cut sparsifiers. So the notion of approximation was the following. I want to build a subgraph H which has the following property. What's the property I care about? I want to make sure that all cut sizes are preserved. By that, what I mean is, look at the cut induced by any set of your choice. Take a set S of your choice. Look at the size of the cut. In a weighted graph, the size of the cut is the weighted size. That is, each edge has a weight, so you look at the weighted this thing. So you look at what you get in H versus what you get in G. And I want this difference, basically this should be very close to each other. So you tell yourself that, I am willing to tolerate like some minor perturbation with respect to epsilon. So I want the ratio of these cut sizes to be like 1 within 1 plus minus epsilon.
So one question. So since we are anyway going to look at weighted sparse graphs, we may as well assume that G.
Yeah, we could have assumed that G was also weighted. And now H, you choose some.
Because this theory doesn't make a distinction.
Yeah, it doesn't really make a distinction. You choose a subset and then you are free to change the weights of G. Okay.
And so what's the motivation behind this?
So what was the motivation behind Ben-Sur and Kargar? Why did Ben-Sur and Kargar study this problem? So basically what they showed in their paper is that there do exist cut sparsifiers that have about n log n edges. Okay, and in fact, they showed that you can do this efficiently. Given a graph G, I can construct a sparsifier with high probability very quickly. Now, what was the point of this? So, for example, suppose you wanted to solve a problem that cares about cut sizes. Like, for example, take something like your max flow problem. You have given a graph G. You want to solve max flow on this graph. Our theorem says that max flow equals min cut. Okay, so I want to compute the min cut on this graph G. But maybe this graph G is just too large. So you could potentially ask, okay, fine, I don't really care about max flow exactly. I'm okay getting a small approximation. I'm like a minor perturbation I'm okay with. So rather than working with G, can I instead work with a sparsification of G, which is H, which is somehow far more something economical in terms of number of edges? Because maybe your flow algorithm you're going to run depends on the number of edges of your graph G, and if the graph had fewer edges, your algorithm may be faster. So there are many instances when you want to solve a certain problem on a graph G, but no, this could be it depends on the number of edges as opposed to number of vertices in some manner. You would like to somehow remove the edge dependency and focus on vertex dependency. So a standard technique there is like, okay, first thing you do is take your graph, sparsify it. And now whatever algorithm you are running, you run on the graph H. And you hope that your answer that you're going to get is very close to the answer you were looking for in G anyway. So max flow is one specific instance that Ben-Sur and Kargar were studying this for.
This just an aside, but this could also be useful for a practical purpose. It might be easier to maintain a sparse network.
That's right. That
has more or less the same property as the ultimate network.
That's right. You should think of this as some sort of a dimensionality reduction that's happening for graphs.
Right.
You are trying to solve some global problem. You somehow try to look at a sparse instance and then focus on that problem. And the guarantee of this sparsification is that the answers don't change.
I have a question also. So how large do the weights need to be on the sparsifier in terms of the original weights? Does it blow up super polynomially?
No, not super polynomially. I think it will have to be polynomial, at least like n or some poly n sort of.
Yeah, but it is.
But the weights don't blow up super polynomial. Yeah. Okay. So this was the main motivation for studying these sparsifications.
Easy to check if the given G and H is edges for.
No, I think that is also NP hard because that looks like you will then be asking for some vertex expansion type statement. So this seems hard here. Yeah, so okay, so this was the motivation for this. This is a specific instance of sparsifier, which I'll call cut sparsifiers. Okay, so
if you just take G to be the complete graph, you're checking the edge expansion.
yeah, right. You're actually checking edge expansion.
Yes.
Okay, so in some sense, a sparsification of the complete graph is a good edge expander. Okay, so that's what you're looking for. And in general, let me write it a little differently. So I'm going to define cut of a set S with respect to a graph G to be the set of all edges such that there's exactly one endpoint that is in S. Okay, and in order to capture this by some quadratic function, I'm just going to build this thing, which I will call Q of QG of X. This is sometimes also called the energy of X. Okay, which is you sum over all possible edges and look at the difference of XU and XV the whole square. And you just add them. Okay, so this is just some expression. And the reason I'm doing this thing is because now if I look at QG on a characteristic vector of some set, this is just going to be the cut size. Okay, this is just a different way of writing what a cut is. I mean, a cut is this particular quadratic form evaluated at the characteristic vector. And so therefore it feels like this quadratic form is something that is very nice, and maybe it makes sense to study this quadratic form. So what we are going to do is ask the question, which is like, okay, this is the quadratic form I care about. I want to know what is the matrix that corresponds to this quadratic form. Okay, there's some underlying matrix which is correspond to the quadratic form, and it feels like that matrix is a useful matrix to know. Okay, and so what I'm going to do is I'm going to write this. I'm going to slowly try and build this matrix, which is I will write this as sum over edges U and V, and I'll write it as X transpose Q U V X, where Q U V is now a matrix that I'm trying to figure out what it should be. Okay, I'm just writing the above sum differently, where X transpose Q U V X, I want this to be XU minus XV the whole square. This is what I want. Rather than looking at this big sum and asking what is the matrix. Sorry, this sum over
the right hand side.
No. So I want to focus on this matrix as only computing one of the terms, and QG of X is the sum of all such terms, one for every edge.
QUV is also a matrix.
QUV is also one matrix. And I'm trying to right. That was the confusion. QUV is also one matrix. So it's a matrix that corresponds to that one edge. And I'm trying to figure out what is that matrix supposed to be. Okay. So in fact, I don't know why I seem to have written it as maybe I will keep it as LUV. So that I stick with my notes. So I want to find a matrix LUV such that X transpose LUV X just computes XU squared plus XC squared minus 2XU XV. So what should this matrix be? So it's basically, if I look at the rows and columns induced by U and V, indexed by U and V, there is a 1 here, there is a 1 here, there is a -1 here, and there is a -1. The rest of the entries are all zeros. Okay. And this is a rank 1 matrix, and which I can write EU minus EV transpose, where EU is the vector that has just one at coordinate U, and so on, and it's just this one rank 1 decomposition. That's what this LUV is, and we'll define L to be equal to, this is the matrix that corresponds to the quadratic form, whatever this matrix is you run through all possible edges and add up these matrices. Obviously, different edges will correspond to different U and V's, and then you add them. Okay. Now, what will this matrix look like? How will you describe this matrix? So let's look at maybe the U comma Uth entry. What will the value be in L? It will be the degree of it, because the 1 will show up as many times as there are edges there. So every other entry that corresponds to an edge, that will show up as a -1. So it's like on the diagonal, you have the degrees, and then otherwise you have -1s wherever there is an edge. So that's the structure of this matrix. And this can be written as the degree matrix minus the adjacency matrix. Okay. And this matrix has a name, and it's called the Laplacian of the graph G. Typically, the way it is usually done is you define the Laplacian as this, and then you derive the above property. But I think this is perhaps a little more instructive as to why you care about this matrix. Like if you care about deregular graphs, for instance, this is like just the flipped sort of matrix. So, for example, if you are caring about the eigenvalues of the adjacency matrix, the eigenvalues of the Laplacian is going to be d minus the eigenvalues of the adjacency, right? So there's a nice. It somehow feels like it captures the sort of notions we were trying to capture. Okay, so this is what a Laplacian of a graph is, and we are going to therefore focus on the Laplacian a lot today. Okay, so there are some beautiful properties that the Laplacian satisfies. Okay, and I'm just going to list down. Many of them will be obvious from just the definition. Some of them maybe require a bit more thought, but I'll let you think about it if something is not clear. Okay, so we know that X transpose Lx takes this form. X transpose Lx is just, it measures this notion of energy, or like look at the pairwise differences across variance across edges, then you sum that up. Okay.
Why is it called energy?
Yeah. So for instance, if you think of your graph as some sort of an electrical network, where every edge corresponds to a unit resistance or something, and the X corresponds to the potentials on each of the vertices. This actually captures the energy of the network that is done in a physical thing, or you think of it as some sort of, you put X sort of tells you where you are placing, you think of each edge as a spring, and then you place it at various places and the energy of the system. So that's the reason why there's a physical interpretation of this. Okay, so the first property is that it is a symmetric matrix. Because it's a symmetric matrix, all our spectral theorem, etc., all work. There's a nice eigen decomposition. Hopefully, the eigenvalues make sense. All of that is going to happen. So, irrespective of whether your graph is regular or not regular, this matrix is always symmetric. Okay, that's property 1. Property 2 is that it's also a positive semi-definite matrix. So, definition of positive semi-definite is that the underlying whatever bilinear form, this X transpose Lx, is always greater than or equal to 0, no matter what X you feed it. And that's obvious just because it looks like a sum of squares. Okay. And then finally, you have a very good idea of what the kernel of this matrix is. If you assume that your graph is connected, ignore like disconnected graphs and so on. Notice that the above sum will be 0. So something is in the kernel means that Lx is 0, which means in particular X transpose Lx should be 0. Right? But look at the above sum and ask, when will this sum be 0? The only way it can be 0 is if all the coordinates are the same. So it tells you that the kernel of this matrix is one-dimensional, spanned by the constant vector. Okay? So that tells you that the kernel is one-dimensional. So it's like not invertible, but there is like a one-dimensional kernel. So in some sense, if you are willing to ignore that part, this matrix is invertible and stuff like that. That is, if you only focus on vectors orthogonal to the all ones vector, then this is invertible and so on. Okay. And then finally, the property that we started off with was that at least in the case of 0, 1 vectors, this bilinear form seems to make sense. In the sense that it captures something that is useful. It tells us that this is the size of the cut induced by such a thing. Okay, so there are some nice properties that this has. So this allows us to sort of rephrase what we want when we are talking about sparsifiers. Okay. So what was a sparsifier? You choose a certain subset of edges, you add some extra weights on top of it. Now let's just try applying that to the Laplacian definition. Okay. So that is, I'm going to now say, I'm going to choose only edges that were chosen in H and take the corresponding terms, but maybe you added your own weight, alpha UV or something for each such edge.
H here is the sparsifier.
H is some sparsifier. That is, so let's imagine that you managed to choose a certain subset of edges and you managed to choose some weights. There seems to be some associated Laplacian, where it's this new term that you have. Okay. And if I were to write it just in terms of what G was and what H was, this is what we started off with. We were given a G, which was like this decomposition. And what's happening in H is I'm choosing a subset of terms, but probably reweighting those terms. But nevertheless, I have one PSD matrix LG. I am building another PSD matrix LH. I'm trying to somehow relate LG and LH somehow. Okay. So what is the cut spacifier condition? It can be stated as saying for all 0, 1 vectors, I want X transpose LHX to be roughly equal to X transpose LGX. Okay, that is, I want it within 1 plus minus epsilon. Now, an obvious generalization is like, why are we restricting ourselves to just 0, 1 vectors? You could say, what if I say that, for all vectors X, I want X transpose LHX to be roughly equal to X transpose LGX. Okay, and these are what spectral sparsifiers are. Okay, these are also sometimes called physical approximations because X transpose LHX in general for an arbitrary X is like capturing energy or something physical about the underlying network or something. So they sometimes refer to this as a physical approximation. Okay, so this is what we are going to try and study. Now note that every spectral sparsifier is certainly a cut sparsifier. Okay, so it's asking for something more than what cut sparsifier gives, and this is actually very useful. And so you could ask the following, let's say you managed to build it. Right now, we have came up with a definition by just generalizing our notion of what a cut sparsification was. But what do we gain out of it? Okay, and you gain a whole bunch of things. So the first thing is, of course, all cut sizes are preserved. Okay, and secondly, if you care about this as a system of equations you're trying to solve, maybe you're trying to solve something of the form you're given L and you're given a vector B. And you want to solve for Lx equals B. Now, turns out the solution for LH equals B is roughly similar to the solution for Lx equals B. So, if you care about finding approximate solutions to linear systems, you might as well solve the LH system as opposed to the LG system. In fact, this was the main motivation for Spielman and Teng to start studying spectral sparsifiers in the first place, because they were trying to find really, really efficient algorithms for Laplacian systems of equations. And in the process of it, they somehow wanted to get a sparsification in that notion. And that's one of the reasons to start studying this thing.
So is every PSD matrix a Laplacian of some?
No, I don't think that is the case, because I'm trying to see why. But I feel like, because I know there are statements that are known for Laplacians of graphs, but not known for general PSD matrices, which is why
eventually some inner product like A, right? It can be always decomposed as some N transpose L.
Right? But because that's just because it's it's anyway symmetric, so you can take the square root of it. And,
okay.
But I don't think it is true that it can always decompose.
There is one restriction.
Every symmetric
So
sum of each row is 0. And
let's say even if you take that restriction, I suspect it's not known, because I think I have seen examples of results that are known for Laplacians of graphs, but not for general PSD.
No, but if it is M transpose Mx, so it's
where M is some symmetric matrix.
Yeah.
In fact,
but then like when you multiply on both sides by A, I try to look at M.
No, I guess Srijanto's question is the M need not have come from a graph.
I know,
Yeah,
but can you look at this as a question? Okay. I mean, does it come from a weighted graph is the right question?
Yeah, weighted graph. But even then, I don't think it is known. But I'll check and get back to you.
Yeah, there is one obvious restriction that sum of which.
Yeah. A PSD matrix where sum of all the rows is, let's say, 0. And the other thing that is also turns out is that this is going to be the more useful notion for us, is that the eigenvalues of LH. I should have written eigenvalues of LH.
Why should some of all those be 0? The graph is weighted.
I mean, the Laplacian satisfies the property that.
Also.
Okay, the eigenvalues of LH are all like very close to the eigenvalues of LH. That is, you just order them and associate each one to the other one, and then they will all be slight perturbations of each other. Okay, so this is also very useful in the sense that if you think about the Laplacian of the complete graph, like there'll be one eigenvalue at 0 and all other eigenvalues will actually be at n. Okay, and asking for roughly the same thing as like saying I don't want one of those eigenvalues to come too close to the same.
The max eigenvalue seems to be.
Yeah. So it's not obvious from just the definition, but if you use this thing called the Courant-Fisher thing, the min-max characterization will tell you that once you know that is true, all the min-maxes will turn out. Yeah. Okay, but at least these are some properties that the spectral sparsifier has. It has a whole bunch of things, like the number of spanning trees in G turn out to be roughly equal to number of spanning trees in H, and like a host of problems. Okay.
Number of spanning trees of H.
Again, each spanning tree you have a weight, and then you sum up over all possible this thing. Okay.
That is a determinant of.
So as I mentioned before, this sometimes X transpose Lx is called the energy of the vector X with respect to the network G, and this is also why these spectral sparsifiers are called physical sparsifiers. So it's like, therefore it turns out that if you think of this as an electrical network, the electrical flow in G is roughly equal to the electrical flow in H, even though the exact paths may be different, but the actual flow is roughly the same, or effective resistances are roughly the same. Like a whole bunch of things hold if you have a spectral sparsifier. All right, so let's talk about what was Bensur and Kargar's algorithm. If you wanted to construct a sparsifier, what do you do? And here is basically what they did. It's the most obvious thing you will try. It's all in the analysis. Okay. You just choose this many edges at random and basically argue using some Chernoff bound type thing that.
Wait, so this is an algorithm for spectral sparsifiers?
No, for cut sparsifiers. Okay, this was for cut sparsifiers. And what they did was they just said, let's just choose a random subset of edges. Okay, each edge is uniformly chosen at random. We'll add that to the graph H. Okay, and everything is going to be reweighted by the edge density in some sense. If the original graph had E edges, you only picked up this many of them. Just rescale every edge by the corresponding quantity. And using roughly like a Chernoff bound and a union bound over all possible cuts, you can show that with high probability, all cut sizes will be within 1 plus minus. So, like for example, if you like the edge density of this new graph is just going to be like 1 log n over epsilon squared. Yeah. Whereas previously the edge density could have been something. So the weights you add on each edge is the right scaling factor so that the final edge density is roughly the same. Just to make sure that you are comparing apples with apples.
So each edge in H has the same.
They all have the same weight. So this is like it's a weighted graph, but it's like it's some sort of global reweighting. There's like not like each edge has a slightly different. It's a completely uniform weighting. Okay. And the first thing we can ask is like, why not try the same thing for spectral sparsifiers and see if that just works. Okay. So let's.
Will it concentration inequalities for lambda 1?
We'll see, but maybe we'll just try out a few examples and see if this is useful at all, and then we'll figure out later. Okay. By the way, so one thing it might be useful to point out is that this property that I mentioned, that it is connected means the kernel of the Laplacian has dimension 1. The more general fact is that the kernel of the Laplacian is exactly the number of connected components. It's the same idea as earlier in the sense that if you take the constant vector on each component, they are independent vectors that are in the kernel. Okay. Okay. So this is going to be useful for what I'm going to say next, is because let's take a couple of stupid examples. The first example we can take is the complete graph. Okay. This is the graph G. And let's just imagine building the Bensur-Kargar sort of sparsifier. So you're going to randomly sample edges of roughly like n log n edges or something. So you will end up with some mess here, but it's a sparser mess compared to what you started off with. Okay. And this looks like a random graph that you build by taking this many edges. And something that we saw earlier is that, this is an expander with high probability.
It's not regular.
Doesn't matter. There's a spectral sparsifier, there's no expectation of regular.
But For expander, first second you can lambda 1.
Yeah, no, I'm talking about an edge expander. This will be an edge expander with high probability. I mean, like, you don't need to, it just feels right that, this ought to be the case. So it's not surprising that this will also be a spectral sparsifier in this case. Okay, it feels like, okay, there is nothing obviously wrong about this approach of picking random edges in this example. Now let's look at the next example, which is the dumbbell graph, where you have two complete graphs on n by 2 vertices. Okay, and there is one bridge edge. Okay, now let's ask ourselves what would happen if I did a random sampling.
If you hit the bridge edge, you are fine. But
Yeah, so within this dumbbell, you're now going to choose a smaller, you're probably going to choose an expander. This also you're going to choose an expander. But this edge, the chance of you choosing this edge is like roughly 1 over n. Okay, because the number of edges that you have is like n squared of them. You are only choosing like, I don't know, n log n edges. So there's a good chance that every time you sample this, you will actually end up missing this edge. Now the point is, this edge is super crucial because the previous graph was connected. So there was one eigenvalue at 0, every other eigenvalue was bounded away from 0. But this graph, if you didn't choose the bridge edge, becomes disconnected, which means now there are two eigenvalues at 0. So no amount of epsilon will tell you that, that is like within 1 plus epsilon of what you started off with. So you need to have some mechanism to somehow realize that this bridge edge is crucial. Whatever sparsification you are going to do, you can't do something completely independently at random. You might have to recognize that there are some edges which are essential, maybe choose those edges, and then maybe you do some random process also. So this is to just point out that, the random sampling method of Bensur-Kargar doesn't seem to work as is. Okay, if you just do, so plain random sampling won't work. Plain of edges won't work.
it is still give an additive approximation.
Sorry?
They still give an additive approximation.
Might give an additive approximation.
Because for each cut you have.
Yeah, so I think this is because something is becoming 0. We were asking for multiplicative approximations, and that just completely fails.
So I have a organization question, which is, so this Kargar,
Bensur-Kargar.
that is already a combinatorial algorithm, which is not a matrix spectral sparsifier.
It's a cut sparsifier.
It's a cut sparsifier.
Yeah.
And so the cut sparsifier question was anyway asked.
Was answered. Yeah. So we.
Why for a cut sparsifier this?
So the point is,
this example.
so the cut size is not like previously the cut size was 1. Now actually cut size also, maybe I wrote it in terms of ratio, so it was a problem.
Yeah.
So I don't, maybe even in a cut sparsifier thing, this is becoming a problem.
Yeah, because if you just take this cut, which has.
If I take a cut that just takes the left half of the dumbbell,
then you will get
one has cut size 0, the other has cut size. Oh, maybe even there's some additive nonsense that's happening. Yeah. Okay. Maybe even there's an issue. Yeah.
So then the Bensur.
So then my definition of cut sparsifier was perhaps a little too general.
Because Bensur-Kargar did.
Yeah, Bensur-Kargar, one of the main questions that they were solving is like an epsilon approximation for the max flow problem. And for that, you need an additive approximation is also good enough.
No.
So here the cut size increases additively it changes additively by just one edge.
Yeah.
So
the question is, did Bensur-Kargar solve the multiplicative cut sparsifier question?
I suspect they did, but maybe the way I phrased it was not the right way of phrasing it. Or maybe they also do this thing of like locating these crucial edges or something. I need to check the.
Not just a random sample.
Yeah, it's not just a random sample. Okay, so now I'm going to restate the problem, and we are going to move away from graphs in general and just start focusing on just, you're given a matrix, you're given some decomposition, I want to find a sparser decomposition. That's it. So here is a restatement. I'm given some matrix L, okay, which is given as a sum of autoproducts, some BI transpose. Okay, what I want to do is find the matrix LH, which is obtained by taking only few of the only few of the vectors that were in the previous decomposition and possibly reweighting them using your alphas or something. Okay, and I want to do this in such a way that I get the following property, which is this particular thing. So let me just define. I will say a matrix A is like at most a matrix, I mean, whatever this norm in terms of a matrix B, this is just a definition to mean that for all x transpose AX is less than or equal to x transpose BX. Okay, that's just a way of, so this is also called the PSD norm. That is, you think of the difference and say that the difference is a PSD matrix.
Sorry, so we are assuming that the matrix given is an honest to God Laplacian.
I'm soon going to not assume that at all.
But then this is why is it
Stronger strange.
So this is a symmetric matrix.
Because the point is, getting a bit confused, because if this L was a Laplacian, then of course the matrix can be written in this way. I mean, any matrix can be written in this way where M is the rank. And you written,
No, M is much larger than the rank.
Yeah, because you want BI.
Yeah.
So then, I mean, okay, M is the sort of the size of the problem corresponding to a graph only when it's a Laplacian.
Yeah, so you should, I'm just trying to abstract out things.
Yeah.
There will be points when I'll keep track of the fact that this came from a Laplacian, but right now I'm just trying to restate the problem in just a matrix language and say that someone gave me.
No, if this was the Laplacian, then it's a perfect.
It's a perfect this thing.
But if it is a general matrix, then it is not. Then this is some strange rank of the matrix.
So this L right now is some symmetric matrix.
So BI transpose is not the spectral decomposition.
No.
BI transpose is some rank 1 decomposition that's given to me, and you're typically interested in situations where M is much larger than the ambient dimension. So M is like the number of edges, which is like n squared.
M could be much larger than the rank of L, right?
Yeah. So M is much larger than the rank of L, and I'm trying to collect hopefully like only order n of these vectors and roughly build the same matrix. Okay, and this is just a restatement of what we said. Probably I'm ignoring some extra conditions that we actually have. So you should be thinking of each BI as basically whatever EUI minus EVI. Those were the vectors, and the L was actually the Laplacian matrix. Okay, but let's for the moment think of it as someone gave us a matrix, a symmetric matrix, and gave us some rank 1 decomposition. Decomposition into a sum of rank 1 matrices. I am trying to choose a subset of that decomposition with rescalings and hoping to build something very close to what I started off. Okay. So the first idea, what the hell happened was sharing stop. Sorry. Okay. I don't know. I think my network dropped or something. Okay, so we seem to be back. The first idea is to just do some algebraic manipulation of this to make the statement a little simpler, which is notice that, if A is less than equal to B in the PSD norm, in the PSD order, then I can take any symmetric matrix and pre-multiply and post-multiply with that. Nothing is going to change. Because, it's the same order will just get, satisfied here. So therefore, if star is true, if star is what I'm trying to get, then I can hopefully choose my favorite matrix, symmetric matrix M, and instead try to hope to achieve something like this. Okay. And what we are going to do is we are going to choose M that simplifies the expression as much as possible. Okay. And the M that I'm going to choose is to make sure that MLGM becomes the identity. Okay. If that happens, then life is a little easier. We can work with that instead. But there is an obvious problem here, which is, one choice of it is what is called the square root of the matrix that you have. I just don't define what it is. But some of you might be wondering, what the hell am I talking about? LG was not even invertible. Right? Because it had an element in the kernel. The kernel had dimension 1. So how the hell can I pre and post multiply with some matrices and get an identity, which is a full rank matrix?
Identity restricted to the
So that's what I should be doing. So basically, in all of this, I basically need to say that okay, ignore what is happening on the all ones vector. Just think of these as operations happening on everything orthogonal to that. Within that subspace, I want to build an inverse or whatever, everything makes sense. This is also called I think the Moore-Penrose inverse. But it doesn't matter. I'm just going to explicitly tell you I'm going to explicitly tell you what this inverse is.
Sorry, so you said if you have that star statement, then the statement is true for any n.
Yeah.
So, but I mean, now you're saying we are going to.
So, for example, if m was also invertible, whatever m I chose was invertible, then these two are equivalent, right? So, I'm going to choose an m that is as good as possible, and that m is just going to be the square root of the Laplacian or the inverse square root of the Laplacian. What do I mean by that? This sort of operations make sense only for PSD matrices. Okay, because your matrix was PSD, it has a whatever eigen decomposition from the spectral theorem. All the lambda i's are actually positive, not negative. So you define the square root to basically be whatever operation you want on each of the eigenvalues that are non-zero. Obviously, the zero eigenvalue you can't do anything about. That leave it as is, but whatever was non-zero, you do the operation you want. Like for example, if you want to do L to the minus half, now I'm just replacing each lambda I by 1 over square root lambda I.
No, this operations of taking square root only makes sense for PSDs.
Yeah.
You have to have non-negative eigenvalues.
Right.
But more generally, for any normal operator.
For any operator, you can do this. Typically, when people talk about the pseudo inverse, what they mean is they just replace each lambda I by 1 over lambda I. So, okay, so this is what we are going to work with. These are some details we need to sort of be comfortable with and move on.
So if you are trying to solve approximate mean cut using this, we need to ensure we can find a spectral decomposition faster than we can find the mean cut.
Yeah, that turns out is possible. Yeah. Okay. So now, this is the m that I'm going to be working with. The m is going to be Lg to the minus half. Now, what do I know? Previously, the decomposition given to me was L is summation bi transpose. Now, what will MLM be? You just write this as summation of MBI transpose, and I'm going to call that as BI transpose. Okay, and this allows me to restate the problem once more. Okay, and this is the final restate, which is I am given an identity matrix as a decomposition into rank 1 matrices. Okay, where it looks like sum over VI transpose, M could be much larger. And intuitively, you should be thinking of each VI as Lg to the minus half of the BI that you started off with. Okay, but this is a new, once you ignore that where it came from, this is what it looks like. And the goal again is the following. Find a subset of these vectors and reweightings such that this new matrix P that you end up building starts looking roughly like the identity. Okay, is the restatement clear?
So once we have found the eigenvalues, why give the decomposition BI transpose instead of the spectral decomposition?
It's because the VIs in some sense is what is encoding the edges in my graph. So the problem I want to solve is something. So I want to choose a subgraph. So this is what is encoding those edges. Okay, so I hope the problem is sort of clear. Okay, so it helps to sort of have a geometric visualization of what exactly is going on. Okay, as I said, there's a lot of setup and there's a final proof which is like very short. Okay, and typically PSD matrices, you try and visualize them via something called a moment ellipsoid. Let me describe what a moment ellipsoid is. Now, given a PSD matrix, there is a natural, functional. The natural form that you have, which is like it takes a vector and returns a real number, which is basically the energy. You take x and you just return x transpose x. Okay, and I want to know what does this particular function look like as I change x in my ambient space. And one way to do this is to study something called the moment ellipsoid, which is you look at your unit sphere And imagine every vector being rescaled by this quantity.
Which one?
The psi v of x. Okay. So the unit sphere is now going to become some weird shape. And maybe I want to just understand what does the shape look like. Okay. And it will turn out to be one nice ellipsoid sort of a thing. And roughly speaking, the aspect ratio of these, how skewed the ellipsoid is, will sort of tell you that like which eigenvalues are large versus small, etc. Okay. So for instance, if your bunch of vectors look like this, okay, and there's a bunch of or I don't know, maybe let's okay, so there's some really long vectors on one direction or something. Now notice that if I had a vector somewhere here, if my x was some vector in this direction, the long vectors are going to contribute a lot of dot product. Okay, so therefore vectors in this direction sort of get stretched a lot. Whereas maybe vectors in this direction don't get stretched by too much or something. Okay, so as you can imagine, the moment ellipsoid of this will start looking a little skewish. I mean, of course, this picture like, sort of is very weird, but this is roughly what I mean. Okay, what's the moment ellipsoid of the identity matrix? It's just the unit sphere. Okay, so one way to restate the spectral sparsifier question is the following. You are given a bunch of vectors v1 through vm, okay, whose moment ellipsoid was the actual unit sphere. It was a decomposition of the identity. Okay, can you choose a subset of them such that their moment ellipsoid sort of looks spherish, in the sense that it contains the 1 minus epsilon sphere and it is contained within the 1 plus epsilon sphere. That's one other way of describing this is what geometrically is happening. Okay, so if you take the complete graph, then the moment ellipsoid is actually the identity matrix up to some scaling, and therefore this will actually look like a sphere. So let's look at what happens in the dumbbell graph. This is a very bad picture. Okay, I am drawing like an n-dimensional thing in 2 dimensions, and like these are all actually different directions, and I'm unfortunately just drawing them in this way. But the point I'm trying to make is the following. If you look at the edges in your dumbbell graph, there are like 3 types of edges. There is one edge which was completely in the left dumbbell. There's a lot of edges in the left dumbbell, in the left whatever blob. And there's a lot of edges in the right blob, and there is one bridge edge. So if you intuitively think about all the edges on the left blob, their coordinates are all within some n/2 thingies. So you should let's group all of those directions as one direction, roughly. I mean, just to get a mental picture of what's happening. So it's like there is a lot of vectors that are roughly pointing in one direction. So I'm looking at each of the vectors, each bi was basically equal to EUI minus EBI. Those endpoints. Yeah. Look at those edges that were in the left dumbbell. They are in some subspace that only involves coordinates in the left half of the vertices. Okay, I'm sort of doing a cartoon by just pointing all those vectors in one direction. That's really not what it looks like, but intuitively, hopefully that makes sense. Okay, then there's a whole bunch of vectors that correspond to edges in the right block. Okay, and then there is one bridge edge which seems to be in a different direction. Okay, and if you think about what is going to happen to this, to the moment ellipsoid, it will sort of look really stretched in those 2 directions. Because, like, for example, if you take a random vector, okay, there's going to be a lot of variance that you end up seeing in this dumbbell and in this dumbbell. So the total energy they contribute will be quite large. Okay, whereas the contribution of this one bridge edge is just a question of xu minus xv the whole squared, where u and v are the 2 endpoints of that bridge edge. So intuitively speaking, things in that direction are far smaller than things in the other direction. I mean, this picture is not too representative, but roughly it should tell you that you should expect the moment ellipsoid of this to be very skewed. Okay, another way to think about it is that
this corresponds like sampling.
Yeah, so exactly, that's what I'm trying to get to. So the other way to think about this is that the dumbbell graph is almost disconnected. It's like it's saving itself from being disconnected by one edge. Had it been disconnected, there will be 2 eigenvalues at 0. The fact that there is this one edge saving it might slightly nudge this eigenvalue, but not much. So if you think of the moment ellipsoid in the direction of that eigenvector, that eigenvalue is really small, so it will be very shrunk in that direction. So there are many ways of interpreting this whole thing. Okay, but the insightful thing is, what happens after this transformation? Everything we multiplied by LG to the minus half on both sides. We had started off with some vectors BIs, which really corresponded to the edges in the graph. But after applying this LG to the minus half, now I have some new vectors BI. And I want to get a sense of what do these new vectors start looking like. So notice, at the end of it, after doing the substitution, the moment ellipsoid became a sphere. So the only way the moment ellipsoid can now become a sphere when it was so skewed earlier is that this operation really stretches that one vector that was that bridge vector. So if you actually do the computation, at the end of this, the bridge vector will get scaled by a factor of n. So in some sense, this operation somehow naturally tells you that which edges are important. The important edges somehow stand out in this picture. The moment you don't look at BIs as a whole, but if you look at LG to the minus half times BI, the length of that vector actually tells a lot about how important that vector is when it comes to these sparsifier questions. Okay, so this is actually what pictorially is happening, but let's proceed with the proof because the proof is not really very far from here. But I hope this sort of rough picture is sort of telling you what's happening. You started off with the Laplacian, which...
What is it theorem?
No, the spectral sparsification theorem. That is this task that I had written down. I need to tell you how to build this B.
Yeah.
Okay. And basically what is going to happen is I'm going to start off with these BIs and do something obvious on top of it. Okay. So good. So I have LG, which is equal to this particular thing. And what I want is to build LH, which looks like sum over BI transpose, maybe with alpha I, but this I just ranging over some sparse set S.
So what special property of BI transpose exactly are we using?
We won't be using anything right now. We will see from the proof as to where that shows up. Okay, the only thing I'm going to really use is actually this is now identity.
Okay.
So
This is the only property of
that's the only property of that. Okay. So natural candidate right now feels to be, why not we build this sum as some sort of a sampling question? Like, let's sample from that sum. But yeah, we understand that all the BIs are no longer of the same length. Maybe the BIs were all of the same length because it had 1, 1 and 1 minus 1. But the VIs will now have completely different lengths. Okay, fine. We'll be a little careful. Maybe we'll sample it according to their lengths or something. And why not just build it using that? And it just turns out that this will work. Okay, and that's the actual proof. The proof is going to be, you take your old edges, apply LG to the minus half. That gives you a notion of lengths for every edge or some notion of importance for every edge. You sample order n log n edges according to their importance. And that turns out that is spectral sparsifier. Okay, that's what we are going to show. And as you can imagine, this is looking a lot like a Chernoff sort of statement, right? But except that we are no longer dealing with normal thing, we are dealing with matrices, right? So what we need is this notion of what is called the matrix Chernoff bound. I'm not going to prove it, but I'll just state it. But I just want to tell you how like sort of similar it is to the standard Chernoff bound. Okay, let's look at what it says. So I have a random variable X, which usually is some real valued random variable, but in this case, it's a matrix valued random variable. And it takes values on D cross D matrices. Okay.
It should be symmetric because
Yeah, so I'm actually going to assume that this is actually symmetric here. In fact, I'm going to say more. I need it to be PSD. Okay.
PSD you're saying.
Sorry?
PSD you're written.
Oh, isn't PSD usually a symmetric matrix?
Isn't U star U dash symmetric? Oh, okay.
Oh,
Yeah.
okay.
Okay.
Okay. So what I want is the following. I mean, I have a notion of what is the average of this random variable. The expectation of this random variable will also be some matrix. It's a D cross D matrix. Okay. And I want that expectation to be identity. Okay. That's the actual average. Okay. And I want each of these random variables to be bounded. Typically in Chernoff bound, you will say that each xi is a 0, 1 random variable and its expectation is something. Instead of 0, 1, I am telling that it's bounded between 0 and m. But of course, everything here is matrices, so I need to write it in terms of the PSD norm. One way to think of this is saying that the ratio of the largest to smallest eigenvalue is no more than m or something like that, but it doesn't matter. Or rather, every eigenvalue is at most capital M. Capital M is some real number, and it's like it gives me some bound on how bad every individual expression of x is. Okay. And now what do I want to do? I want to sample from x, I don't know, k times, take that average, and I want to compare that average with what the actual expectation is. So this is like the empirical average, like 1 over k times summation xi, if I take k samples. And I want to compare this with the identity matrix. And I want to say these two matrices are close to each other. Now, what is one way of saying close to each other? We've already seen this notion of a spectral norm. That is, how much does this matrix stretch any vector? Okay, and I want to say that the chance that there is still a lot of thing left compared to the empirical average versus the actual average, that the resulting vector has an epsilon mass anywhere. I want to say this is very small. You should think of this as saying that the length of this times a certain vector y is roughly the same as the length of 1.
That's the spectral norm, right?
This is the standard spectral norm.
So I think these concentration equal for any matrix between the of I, as long as I eigenvalues are.
I thought this you'll have to change the right hand side appropriately or something.
So,
but this is in some sense the cleanest thing which just perfectly works for the setup we are in.
So the property that of I that we will use here is that if the matrix, the difference of the matrix and I has small of I unknown, then actually the PSD order is also automatically close to I. Is that the property of I?
So here the only property that I'm now going to use is like this. Like for example, if this does not happen, that is, if this was less than or equal to, then you automatically have.
Yes, this is the property of I, in other words, of VI transpose.
Yeah. Oh, okay. Oh, you meant that way. Actually, yeah, that's it. Okay.
So what is capital M?
Capital M is some number. It's some number. Yeah. Okay.
I suddenly thought that capital M was popped in there.
No. So it's some bound that I have, and if this does not happen, then this you get the thing that you want, because this will roughly tell you that this behavior on any vector y is roughly the same as identity's behavior on y, which means the moment ellipsoid looks roughly like spherish. Okay, so therefore we just need to set up to use the matrix Chernoff bound, and then the rest of it is done. Okay, there's going to be, I don't know what this M is going to be. I don't know what K is going to be. D is going to be the ambient dimension, which is like N or N minus 1 or something. Like if the matrix L that we started off with was an N cross N matrix, then this is the ambient dimension. Okay, so now we have everything that we want, and I'm just going to use this. So I was told that I equals summation VI transpose. Now I want to first build this random variable x. Okay, I want to build this random variable in a way that its expectation becomes the identity. Okay, so one choice for this random variable is that you basically take each term with a certain probability and you arrange for it in such a way that the expectation becomes the sum. So you fix some pi for each of the m terms that are there. And you say, I will take this particular vector, VI transpose, like 1 over p times that, with probability pi. Okay, and this is just to set up so that, what is the expectation of this random variable? Well, it's, what did I do? Well, it's going to be with probability pi, it takes vi transpose by pi. And this is just summation vi transpose. And this was the identity. So the expectation is the identity. Okay, good. The next thing I want to do is, the smaller I make this number m, whatever this number is, I get better bounds. Okay, so I would like, right now, this whatever I have written so far works for any choice of pi you would want. Okay, but I would like to somehow minimize m, and this is where the choice of pi is going to become random. Okay, that is like in Chernoff bound. If every single random variable was too spread out, then obviously your concentration will become weaker. So I would like to choose my pi such that none of these matrices are sort of too spread out in that sense. Okay, and so one natural candidate seems to be something that we thought about earlier, is that I want to choose the edge corresponding to the length of that di. Right? Okay, length squared, because I don't want to deal with square roots or something. So this is one candidate. So let's just try to measure how well does this candidate do. Okay, so what is this going to be? So therefore pi is actually equal to the following. So it's vi squared by summation vj squared as I range over all j's. That's the exact probability by which I'm going to choose the vector vi. Okay, and sorry, so now what I want to do is I just want to get a sense of what is summation vi squared or vj squared. Because that's what the denominator is. And I'm trying to get a sense of that. Okay, and here is a trick that I think people who work with these matrices and so on, this just comes so naturally, but this was something that was non-obvious to me, which is, you notice that vj squared is nothing but the trace of vj transpose. Because that's what is on the diagonals. And this is one way of writing it. The advantage of writing it as a trace is that you can now swap the outer summation with the trace. And this is the same thing as trace of summation vj transpose. And summation vj transpose was identity. So if you are dealing with n-dimensional matrices, this is going to be n.
N-1 is identity for n-1.
So let me use capital N for the number of vertices in the graph. The way I have phrased it, I have some decomposition of the identity of the n cross n identity with something. So I'm just writing it this way. So what does this say? That this tells us that if each pi squared is basically equal to the length of vi squared divided by n, because that's what the denominator is, just n. Okay, good. So now I need to get a sense of what m is. What is m going to be? M is going to be the okay, what was m here? M was an upper bound on each of these matrices norm. Okay, and each of the matrices we are talking about is just a rank 1 matrix. How large is the norm of this matrix? Well, this m is nothing but going to be the max of vi squared. What do I want to say? So I want to say this is a max of vi squared divided by pi. Right? And this is exactly equal to n. Because pi was nothing but, again, whatever. Pi was, where did I write pi? I thought I wrote pi somewhere. Oh, I don't know why. I just wrote it in the wrong place. Okay, so it's the max of vi squared over pi. Okay, and we just set it up in such a way that this was actually equal to n. So now we know all the all the terms that we needed to fit into the matrix are now formed. Okay, you have now come up with a random variable x with the property that each xi is between 0 and n times I.
in this group. So, yeah, so the summation of the VJ square is n, and pi is that.
So, okay, so
So it's actually for every one of these, this is.
yeah, so in fact, all of them it's actually n. So it's the max of vi squared over pi, which is max of vi squared over vi squared times summation vj squared, and this cancels off and you get n. So the max is the same throughout. I mean,
This wrote pi over vi squared by n on the left.
okay, clearly I just completely missed it. Okay, so now let's just plug this in and see what we get. Okay, how are we applying the matrix Chernoff bound? Let's write. So this D, this D is basically n cross n now. Okay, this M is actually n now. Okay, and so therefore, when I plug this in, what am I going to end up getting? So I'm going to get 2n times exponential in minus epsilon k squared by 4n. Epsilon squared k by 4n. Okay, and if k is equal to order n over epsilon squared log n, then one n cancels off, the epsilon squared cancels off. This looks like an exponential in log n. That is enough to kill the n that is sitting outside. Okay, so therefore, this is going to be, I don't know, something like at most 1/3 or something. I mean, the chance of you not getting this sort of concentration is like at most 1/3. Okay, so therefore, there are, or rather, therefore, a random subsum satisfies star. Whatever the sparsification question that we wanted to do, this says that this random sampling process actually solves the sparsification question. Okay, so just to put the overall algorithm for spectral sparsifiers, this is how the algorithm goes. We were given a graph LG, and the natural decomposition was you have a decomposition based on rank 1 matrices, one for every edge. Okay, that's what we are calling BIs. So the first thing we do is compute the VIs, which is the LG to the minus half times BIs. Okay, and now think of that as your weights for picking the ith edge, and sample k edges according to that probability distribution. The probability distribution proportional to the length of BI squared. Okay, and every time you pick up an edge EI, you put its weight to be 1 over pi, where pi is that quantity. And that's it. You've now taken a collection of k edges, call that your weighted graph H, and say that's the sparsifier. Okay, this is the Spielman-Srivastava algorithm. It turns out, sorry, the factor of log n is coming from the factor of n in the matrix Chernoff on the outside. That is this factor of n on the outside. Actually, that's a very good point. Actually, the factor of d on the outside is necessary in the matrix Chernoff bound, because notice that you can take your standard Chernoff bound and think of d cross d matrices where you just repeat that entry d times on the diagonal. So you have to lose a little bit. So the factor of d outside is sort of unavoidable. Yeah, and that extra log n is coming from that. Yeah, that's right. Okay, so going back to Srijata's question, okay, this is all an algorithm. It tells us that spectral sparsifiers exist. It gives us a randomized algorithm to do this, but on the face of it, it looks like this randomized algorithm will take too long, because it feels like I need to first compute LG to the minus half and stuff like that. But apparently, apparently it turns out that this algorithm can actually be done in something like m square root log n time, which is like faster than sorting m things. Okay.
And is what the number of edges. So
M is the number of edges. Sorry. that is the initial decomposition is m things. Yeah, sorry. The initial decomposition is m things. And so it turns out you can apparently do this in m square root log. By do this in the sense that you only need the lengths to get a sense of, to sample the ith edge, I need to get a rough approximation of what that length is. Length of vi squared. And apparently this can be done in m square root log n, roughly. Okay. So this is super efficient algorithm. And then subsequently, there was actually a paper of Batson, Spielman, and Srivastava, which actually shows that there are spectral sparsifiers where you don't need this factor of log n. You actually just get n over epsilon squared edges, some constant times n over epsilon squared edges. And this is a very iterative process. Basically, what they show is that every time they try to figure out what vector should I add. And they somehow try to make sure that if adding one vector makes the sphere aspect ratio a little larger, they compensate for it by adding the next one. It's a very nice potential function argument. But it's not a random process in that sense. I mean, in the sense that it's a way by which you need to take each of the vectors you currently have at your disposal and get a sense of what is the best vector to add. And they show how to do this. If I remember correctly, this is not as fast as this. So we don't have a near linear time implementation of this. If I'm at least.
But this is a de-randomized, right?
Yeah, this is it really tells you the quality of adding the VIth edge and so on. But it's
this one we use
yeah. So so there are videos. Piyush's course has videos on the Batson, Spielman-Srivastava thing. But this is also a really beautiful algorithm. That actually, in fact, it's more physical in the sense that the intuition really comes from you put eigenvalues on some inclined plane, like imagine them as charges, and then you add new charges, and then the eigenvalues move a little, and it's a very visual algorithm to see the thing. But that's not something that we're going to be doing at all here. Okay, so since I mentioned effective resistances, I will just say this one thing. So notice that the importance of, we chose the edge E according to the norm of the norm square of Vi. Okay, and the norm squared of Vi, let me just write this here. The norm squared of Vi, this is nothing but norm squared of Lg to the minus half Bi, because that's what Vi was. Okay, and this is the same thing as Bi transpose Lg inverse Bi, because Lg to the minus half twice will become Lg to the minus 1. Okay, now turns out this has a very nice physical interpretation. Okay, so Bi is like saying if it's the UVth edge, it has 1 in the U position and minus 1 in the V position. That's what that looks like. Now imagine that as that is the sort of current flowing in the network. Like you have a network and then you connected the UV edges by 2 wires. And there is 1 unit of current flowing into you, and you're pulling out 1 unit of current out of you. Okay. If you think of that as the description of what this vector looks like, what you actually measure here is the effective resistance of this edge UV. Okay, and I'll
sorry, can I explain that again?
So basically think of your graph G. Okay, this UV is one such edge. Okay, basically I'm saying imagine connecting a battery to U comma V, where now U has, I'm trying to pull out one flow of, or rather I'm giving U a potential of 1 and giving V a potential of minus 1 or something. And I'm just computing how much current is flowing through that circuit.
No. Okay, and the edges have what resistance?
All edges have resistance 1.
All edges.
If it's a weighted graph, the resistance is like proportional to the weight, but otherwise the edges all have resistance 1. And now this is the picture, and you can ask how much current is flowing through this circuit. Turns out that quantity is exactly this. It's bi transpose Lg to the -1 bi.
Just the
No, where is- where is-
give you a system of equation for each.
Yeah, so if you write down that, basically
Basically,
you'll end up with the
I'm
same.
getting confused by something. So, but here you just said it's all normal, right? So you're just saying one, your potential difference of E, the potential difference is 2 volts.
Yeah, it's 2 volts, say.
2 units.
Okay, 2 units or something.
Yeah.
And you're asking how much current is flowing through the circuit, because that's going to be the effective resistance of this edge. The more resistance there is, there'll be
Oh, the
less.
VI is entered because of the VI is what's placing the.
Yeah, so in the sense that the bi was a vector that had 1 in the uth position and -1 in the vth position. I'm interpreting that as saying u has a potential of 1, v has a
No, I
potential.
understand, but I'm just saying, where does this VI, the decomposition that you have, where did that enter?
No, it's just okay. So there are 2 separate things. So for example, if I give you if I connect to 2 endpoints of an edge by a battery and ask how much current is going through it, the way you will compute it is by actually computing this quantity. Turns out, if you actually work out the calculation, that's what it turns out to be. Our definition of VI somehow satisfies the property that the square norm of VI is also equal to the same quantity. So another way of interpreting this algorithm is you pick up an edge proportional to its effective resistance in the network. That is how you build a sparsifier. So you build your spectral sparsifier by first computing the effective resistances of every edge, and then you build one. So just to get since I have some time, hopefully, that I will tell a little bit about this, is that let's imagine this dumbbell graph. Okay. Now let's just imagine that every edge is given a resistance of 1. Okay. I want to know what is the effective resistance of this edge. So that is, if I connect those 2 by to the endpoints of a battery, what's the resistance going to be? Well, the fact that there is a dumbbell on the left and the right is sort of irrelevant here. So the current is just going to flow through this one thing. So the effective resistance is actually 1. Okay. Okay, good. Now let's take 2 things here, maybe some 2 vertices here, and connect those 2 by an edge. And I want to know what the effective resistance here going to be.
Yes, it's a system of equation for the potential of equation.
For now, let's say we just want to get a sense of a rough estimate of what do we expect it to be. So if I focus on this, one subgraph that I have is the following. So there is this one edge, and then there are sort of lots of triangles like this, right? Because to go from this vertex to this vertex, I could have gone to any other vertex and then come back. So this is like a sub network inside the whole network. And if you compute what the effective resistance of just this sub network is, okay, that's already at most like so this is like something like 1 over n or something, order 1 over n. So you can do this for the whole network or something that you want, but it should roughly tell you that the edges within one of the whatever 2 blocks, their effective resistance is really small. So the length of the VI is already telling you that the bridge edge is n times more crucial than any of these other edges. And that's sort of what the algorithm is sort of doing. So this is another concrete way of. Okay.
But there's no sort of a physical or like a localized explanation of this, right? Because it turns out that it's like an thing, the resistance.
So, but what do you mean by a local? Yeah.
There's like some sort of physics based, like the Kirchhoff law kind of based explanation of the whole thing.
Yeah, so it's just that the once you write down that system,
like right now this happens.
yeah, it's just that the Laplacian is awesome in that sense. I mean, it turns out the system of equation that you end up getting is precisely this.
And so do the blower box for CSS, you need to choose at least this many this.
So actually, I don't know off the top of my head, but somehow it feels like n over epsilon squared is the right answer. I don't have a good explanation as to why I think so. This must be somehow connected to this, the Ramanujan 1 over square root d thing also, I presume. Yeah. So anyway, so one way to build expanders could be to you just run the sparsifier algorithm. You don't change the number of vertices at all, but at least you reduce the average degree.
And then you're just randomly, if you are starting from a complete graph, you're just randomly sampling.
There you can just randomly sample, but yeah, so that's one. No, I was just
BSS is deterministic.
BSS is deterministic. Batson Spielman-Srivastava, that is deterministic. Yeah, but it's not a quick algorithm. Since that it's not.
It does not give you regular graph.
I think neither of them give regular graphs.
Yeah, you also don't have control of the degree.
Yeah. So I mean, like, okay. By the way, this is a whole rabbit hole. Okay, I mean, like, in fact, you can really see Spielman and like Nikhil Srivastava and so on going down this. So Spielman and Teng they wanted to do Laplacian linear solvers. They wanted to do those quickly. So spectral sparsifiers seemed natural. So they solved the spectral sparsifier question, and then there were two things that were a little annoying about it. The first thing is that it has this extra log n factor. And the natural question is, do you need this log n? Can you get rid of that log n? And then BSS said that no, yeah, you can actually get rid of that log n. So that log n was. The other annoying factor is the fact that do you really need weights? If my original graph was unweighted, ideally speaking, I should be able to get an unweighted graph H that I scale like by some uniform weight. Okay, so because this way of doing it, I need to somehow each edge is stretched a little bit more. Like even if I start off with an unweighted graph, it's like I'm adding weights that are not the same across all the edges. So natural question is, can I actually do this by actually having a uniform weight throughout? Like every edge is scaled by the same amount.
Well, basically, unweighted.
It's basically an unweighted graph going to an unweighted graph.
And then you're saying you will select the dumbbell edge.
So, okay, or I should in fact state, maybe in terms of the dumbbell, it's one needs to state it properly. I agree, the dumbbell is a problem. So basically the question I want to ask is the following. That is, I give you a decomposition of this sort. Okay. Can you find a subset such that without these weights, this looks like a scaling of the identity? Like maybe it looks like half the identity or something like that. Okay. Now, as you point out, there are issues with respect to this because the dumbbell graph seems to have a problem. So you need to somehow say that each of these VIs are not too large. In a dumbbell graph, there was one of these VIs had length n. So if you assume that all the VIs are small, you're asking if I have a lot of VIs that add up to the identity, can I partition them into two subsets such that each of them add up to roughly half the identity? Turns out this problem is equivalent to something called the Cadison-Singer problem. Okay, that you're given a bunch of VIs, all the VIs are small. None of the VIs have too large a norm, and they add up to identity. And you're asking, can I partition them into two subsets such that each of them roughly looks like identity? Okay. Turns out that is very closely related to, if you start off with a complete graph, can you get these Ramanujan expanders by this sparsification method and so on. So that was the reason why Marcus, Spielman and Srivastava were looking at this unweighted question, and they eventually resolved the Cadison-Singer question and so on. And that's a really large rabbit hole. Like you start off, you notice that in Batson, Spielman, Srivastava, the key idea there was some notion called interlacing. And then they explored that idea more and more, and they were actually able to solve the Cadison-Singer question, which is what I briefly mentioned. So I think Piyush's course must have covered a lot of ground on that. So I would highly recommend that people try. Okay, good. So that's
this was a small course on polynomials.
Yeah, there were some zeros of polynomials. Yeah. So, okay, so this will complete the module on expanders. we will still occasionally revisit them to get inspiration in the subsequent modules and so on. So in the next class onwards, which is Tuesday, we will start on this module on error correcting codes. And yeah, then we'll see how it goes. And definitely by this weekend, I will put up a problem set. I think something or the other keeps coming and I haven't been doing that. Okay. Okay, then we'll meet on